So we talked about budgets for CO, methane, and hydrocarbons. This is a budget for tropospheric NOx, formation and coupling. And the global sources are given here: fossil fuel combustion, soils, ammonia oxidation, and transport from the stratosphere. And notice that fossil fuel combustion is the biggest contributor to NOx. So if we can control NOx emissions from combustion, then we can significantly reduce the burden of nitrogen oxides in the atmosphere. And I'll give you some data on that later on. The other source is biomass burning. Again, that biomass burning is forest fires, lightning. So lightning is a significant source, interestingly significant source, aircraft, etc. We've talked about the ways in which NOx reacts, and there is a very strong coupling between NO and NO2 and also ozone, and its time scale of about a minute during the day, especially in polluted regions. And so NO reacts with O3 to form NO2 plus O2, and then NO2 gets photolyzed, O reacts with O2 to form ozone. And there's also a reaction HO2 plus NO converting NO to NO2. So this is termed the photochemical stationary state is established between NO, NO2, and ozone because of these effects here. Interestingly, the concentration of ozone in the middle of cities where NO is high is significantly reduced because of this reaction here. So it generates NO2, which in turn regenerates ozone, but nevertheless, this photochemical stationary state, when NO is high, is moved over. So here's loss of NOx, OH plus NO2 plus M forming nitric acid, rain out of NO3, also dry deposition, and conversion into other forms of oxidized nitrogen, for example, organic nitrates. The lifetime of NOx is about a day overall, so that's the coupled NO-NO2, and it's a key species, as we've said, in ozone formation. NOx, as we've seen, is primarily emitted in regions where you've got significant amounts of combustion. So this means that it's going to be higher in populated regions, but can it be transported to other regions, given that its lifetime is comparatively short, lifetime of NOx? Well, what can happen is you can get the formation of a species called PAN. So just let me give you one source of PAN. If you take, say, acetone, this gets photolyzed, so interaction with a light photon, and it forms this acetyl radical, which reacts with O2 to form a peroxy radical. And that then reacts with NO2 to form this species PAN. So PAN is peroxyacetyl nitrate, CH3COO2 NO2. It's brown in color, and in a polluted region on a nice sunny day, you can often see a band of brown in the horizon, and PAN is contributing to that. Some NO2 is contributing, but PAN is also contributing. And PAN dissociates to regenerate acetyl plus NO2. So at normal temperatures, what happens is the PAN simply dissociates back again to form the peroxyacetyl radical plus NO2. But it can be lifted up into the atmosphere, and there the temperature is lower, and so that rate of dissociation is considerably slowed. And then the pan can be transported over quite long distances before it eventually subsides, and as it subsides, the temperature goes up and it dissociates. So because of that dependence of this dissociation rate constant on temperature, pan provides a means whereby NOx can be transported from regions of high emissions to regions of low emissions. I apologize that these are European values and not American values, but this shows you the way in which NOx emissions have been reduced between 1990 and 2005 in Europe. So there's been some reduction. This is what the NOx emissions could be. Sorry, that's what they would be if we had carried on as we were operating in the early 1990s. This is what's actually happened. So the NOx is lower overall and has been reduced over that period of time. And this is by applying some of the techniques that we talked about yesterday, using selective non-catalytic reduction, using reburn, using especially catalysts on cars. But we could have done much better if we'd fully applied the techniques that are available for reducing NOx. So we could have been in this sort of situation if over this period of time we'd applied all of these techniques. This is the UK, and so this shows the different sectors contributing to NOx. So here's road transport, public power, industry as the main contributors. You can see that public power has gone down significantly, and road transport has also gone down. This is despite a significant increase in the number of vehicles on the road. The emissions of NOx have gone down because of the use of three-way catalysts. And overall, the amount of NOx has gone down. And so that was up to 2000, and this is going up to 2010. And you can see that NOx is continuing to decrease. Sorry, this is NOx coming from, these are entirely from transport. So big reduction in cars, smaller reductions in other vehicles. So this is 2002 to 2010, kilotons of NOx emitted from road vehicles in the UK. Now, let me show you what I think is a beautiful analysis of formation of ozone. It's from a book by a man called Daniel Jacob. And he's at Harvard. And being an exceedingly magnanimous person, his book is available on the web. So you can just go and download the whole of his book or just read the book on the web. But he's one of the leading modelers, atmospheric chemistry modelers. So this is the scheme that we had before for hydrocarbon, and the initiation process he's called POH, and that's given by J1 ozone, which is the photolysis of ozone to produce O singlet D, and then this ratio 2K3 times water, which is O singlet D plus water, giving 2 OHs, so that's why the 2 is there, and that's divided by K2 times M plus K3 times water. So this is the rate of removing O singlet D. Total pseudo first order rate constant with the removal of CO2. And this is basically the fraction of the reaction multiplied by 2 that goes from O singlet D to OH. So that's the rate of production of OH. Then we've got the propagation steps, OH plus RH plus O2. So when I've put O2 in brackets, that's signifying that there are really 2 reactions occurring in sequence. first of all, the generation of R, and then all that R does is reacts with O2 to form RO2. RO2 plus NO, RO plus O2, HO2 plus NO, and these are the reaction numbers. So this is the propagation cycle, and then termination, and he's just simplified this to HO2 plus HO2 going to hydrogen peroxide, and OH plus NO2 going to nitric acid. Then ozone is formed by NO2 photolysis with a rate equal to the sum of these two reactions. So the presumption is that once NO2 is formed, then it photolyzes to form ozone. And Jacob also makes the assumption, and it is an assumption, that the chain length is long. We know that the chain length isn't always long by any means, but that then enables him to use simple chain reaction rate theory. Okay, so here's the analysis. So under polluted conditions, chain propagation is fast, and so these chain propagation steps, so each of these chain propagation steps have equal rates. So the rate of step 4 is the same as step 5, step 6, step 7. If that weren't the case, then one of the species in the chain cycle would build up. So they all have to be the same. And the rate of forming ozone is equal to the rate of those two steps forming NO2. Since these are equal, we can say it's equal to 2V7. So it's going to be equal then to 2 times K7 times HO2 times NO. And let's call that equation A. In addition, V4, this step is equal to the rate of this step here, because they're both propagation reactions. So we can equate those, and OH is going to be equal to K7 times HO2 times NO divided by K4 times RH. So that's the rate of forming OH from HO2 and the rate of removing it, or the pseudo first order rate constant for removing it by reaction with RH. We have a steady state for radicals, and so the rate of termination is equal to the rate of initiation. They're straight chain reactions. The overall radical concentration is maintained, so the rate of forming radicals is equal to the rate of removing radicals. As a kineticist, one can criticize this analysis, but it leads to very, very nice understanding of what's going on. So steady state for radicals, rate of termination is equal to rate of initiation. So POH, the rate at which OH is formed, is equal to the sum of the rates of termination. That's HO2 plus HO2 and OH plus nitric acid. If we work at low NOx, then V8, this step is very much faster than this step here. So these are low NOx conditions. V8 is very much greater than V9. So rate of initiation, POH, is going to be equal to 2 times K8 times HO2 squared, because two radicals are removed from this step. So HO2 is equal to the square root of POH over 2K8. We substitute that in equation A. We get that the rate of forming ozone is equal to 2K7 times NO times the square root of POH divided by 2K8. So what that tells us is that the rate of forming ozone is proportional to the concentration of NO, and it's independent of the concentration of the hydrocarbon. And we call these NOx-limited conditions. On the other hand, if we go to high NOx, V8 is very much less than V9. So this is now the fast termination compared with that. So OH now is equal to, using the same idea of termination and initiation, to POH divided by K9 times NO2 times M. Substitute that in B, and we get that HO2 is equal to P. I won't go through this in detail, but this is the result that you get, is equal to POH times K4 times RH over K7 times K9 times NO times NO2 times M. Substitute that in A, and you get this expression. The rate of forming ozone is equal to 2K4 times RH divided by K9 times NO2 times M. So the rate of forming ozone now, under high NOx conditions, is proportional to 1 over NO2 and proportional to RH. And we call this VOC limited. So those are a couple of useful results which tell us about what are the key species in terms of forming ozone under high NOx and under low NOx conditions. And it also tells us what we should be doing in order to control the NOx. So this is a summary of what's going on. So this is the rate of forming ozone under VOC limited depends upon RH, and it depends upon the inverse of NO2. Under NOx limited conditions, it's independent of VOC and proportional to NO. So you need to understand what's the chemistry that's driving the rate of forming ozone. So are we under NOx limited or VOC limited conditions? If we're under NOx limited conditions, then there's no point in reducing the VOCs. One of the regions in the US where ozone concentrations can get quite high is the southeast. Those of you who come from Georgia Tech will know that ozone can be quite high in Atlanta. And there it's definitely NOx limited. You get very big emissions, a lot of deciduous trees in the area, and you get a lot of emissions of isoprene in particular. So there's a lot of VOCs around, and it's definitely NOx limited. So if you want to control the ozone, then the route you need to take is to control NOx. On the other hand, if we go to the UK, we have very few trees in the UK. And there we're VOC limited, and you need to control the VOC emissions from vehicles. This is what's called an ozone isopleth diagram. What it shows is the amount of ozone that's formed as a function of NOx emissions and hydrocarbon emissions. If we're down here at low NOx, then you can see that if you keep NOx constant and you increase, if you keep NOx constant and you increase the VOC, the hydrocarbons moving up in this direction, you don't really affect the ozone concentration at all. On the other hand, if we're over in this region here where we're NOx saturated or VOC limited, if we increase the hydrocarbons, then ozone goes up. If we increase the NOx, then the ozone goes down. So this diagram and this analysis is a nice, simple way of understanding the way in which you might use policy. And this diagram has been used by the EPA to understand the ways in which you need to have some general understanding. I mean, they do very detailed modeling, but this has enabled the EPA to do quite a lot of understanding of what's going on. Here's the global budget for ozone in teragrams of ozone a year. Chemical production, 70% from HO2 plus NO, 20% from CH3O2 plus NO, and 10% from RO2 plus NO. So this is reflecting the fact that over much of the surface of the Earth, then it's really methane and CO that are dominating the chemistry. Transport from the stratosphere makes a small contribution. And then this is the way in which ozone is lost. Ozone at E plus water is the photolysis route, then HO2 and OH plus ozone. And these are important reactions in really quite clean conditions. So working in Tasmania, we found that both of these reactions were quite significant. And then finally, dry deposition. Ozone is taken up by plants, and it causes damage as that happens. But that's one of the key ways in which ozone is removed from the atmosphere. Here's a picture of the global budget. Hydrocarbon emissions, these chemical cycles, deposition here, exchange from the stratosphere, chemical production, chemical loss. It's a nice little picture, but we've really discussed all that's in there already. This is an interesting diagram about formation of ozone in Western Europe as a function of time of year. So this calculation was done in 2006. So this is ozone formed regionally in Europe. It's a regional process because of the timescales that are involved. We've said that something like isoprene reacts very rapidly in something like 3 hours, but other species, it takes many, many hours or even days for the reaction between OH and the VOC to take place and the chemistry to happen that generates ozone. And as we'll see, there are several generations of reaction that take place. So it's a regional process, and ozone formation takes place over hundreds and even thousands of kilometers. And so this is ozone formation in Europe on that sort of time scale. And then these are contributions that come to Western European ozone from North America, from Asia. This is intercontinental Europe, and this is and then extracontinental. So this is coming from Europe, and it's gone right round the globe. So the ozone precursors have started off in Europe, and then transport has taken them right round the globe. But you can see that there's a significant amount of ozone that's formed from emissions in North America and also from emissions even as far away as China. And this is transport from the stratosphere. The regional ozone peaks in the summer because it's photochemically derived. The transport that's hemispheric is much more evenly spaced throughout the year. So the take-home message from that diagram is that ozone formation is a hemispheric process. It's not just regional. It's not just occurring over the region of Europe, for example, or over the region of North America, or over the region of China. It's taking place hemispherically. So we call this sort of hemispheric ozone background ozone. And so what's happening to background ozone? And this is a selection of results. These were measurements made in Paris at the end of the 19th century, and ozone was in the range 5 to 16 parts per billion. This is ozone in Switzerland in the 1950s, where concentrations doubled over a period of 30 years. Ozone sondes in the northern hemisphere show increases in the 1970s, but no clear trend in 1980 to 1996. Ozone sondes in Germany, large increases in the 1960s to 1980s, smaller increases, and even declines thereafter. Surface ozone, 17 background stations, no clear or consistent trend, even in northern latitudes. Background ozone has increased by up to 5 parts per billion per decade over the last 20 to 30 years, according to measurements at sea level and on mountaintops that are less influenced by European sources. So what this is saying is that, and this is a European perspective, is that if we look in continental Europe, then the ozone isn't really changing particularly dramatically. But if we go to the west coast, if we go to the west coast of Ireland and screen the results so that we're only seeing ozone under conditions where the air is coming from the west and not from Europe, if we screen the results so we're only looking at where ozone is coming from the west, then there is some evidence of increases in the background value. And so this is a trend at this place Mace Head in Western Ireland, and these are screened So in other words, these are ozone concentrations under conditions where you've got a westerly airstream, and the air is not impacted by emissions from Europe. And there's a bit of a, unfortunately, there weren't measurements made before 1987. It would be nice to know whether this is an outlier or not. But you can see that there is some sort of increase over this period of time. And this corresponds to about 35 parts per billion. There are different units that have been used here, micrograms per meter cubed. But this corresponds to about 35 parts per billion. Now, just think for a moment about the consequences of that. The so-called limit value used in the UK for ozone is around about, is 50 parts per billion. And yet the air that's coming in, even under clean conditions from the west, is of the order of 35 parts per billion. So our emissions and the emissions in Europe can increase that ozone by a relatively small amount before we begin to exceed the limit value. The European value is 60 parts per billion, and that European limit value is a legal limit. We are required, countries of Europe are required to stay within that limit value. If they exceed those limit values, then we can be prosecuted by the European Union. And so 35 ppb, 60 ppb, there's not a lot of difference that can take place. What's happening in the US? So it's not terribly clear. This is a place called Trinidad Head, and there is some evidence that to suggest again that the background of ozone coming into, or the background ozone due to emissions from remote sources is also increasing. Background ozone is primarily determined by NOx, CH4, and CO. So limiting these provide the best policy options for controlling this background ozone. So what's going on? So these are data from an organization called IASA in Austria. And what they do is they look at trends over the next decades of emissions of these various species. And so this is taken from a report to the Royal Society, and it's primarily looking at emissions. This is looking at policy for road vehicles in various countries. This is the European Union at the top, and these are various standards for emissions for road vehicles, for for both gasoline and diesel vehicles. And so different countries, you can see, for example, China, there are very substantial controls being effected. This is going up to 2014, and very substantial controls being effected in many of these countries. And taking this legislation, which is operative in all of these countries, this is a prediction on what's going to happen as far as NOx emissions are concerned, going out to 2100. So the projection is that NOx will decrease. This increasing line here is a line that went into the fourth assessment report of the Intergovernmental Panel on Climate Change, which I'll talk about in a little while. And there, this new legislation wasn't appreciated, and so these are the reductions in NOx which it suggested will take place because of the sorts of controls which are being implemented, especially for road vehicles. This is methane, and this is the fourth assessment report of the IPCC, And this hasn't really changed. And so you can see emissions from, here's Europe, from the former Soviet Union, North America, Asia, and the rest of the world. And you can see these substantial increases in methane emissions from these two regions here that are projected. So these are, as I say, projections. These numbers down, these labels down here, A2 and B1, these are what are called scenarios, which are used in projecting what's going to happen with climate change.
Question.
Yep.
Is the use of natural gas in power plants shift towards natural gas going to increase the methane emissions? Has that been taken into account?
Oh, that has certainly been taken into account. I mean, the methane emissions using natural gas as a power source is primarily from leakage and losses of methane. But that has been taken into account. Regional air quality. This is the World Health Organization Air Quality Guidelines from 2005, which apply in principle worldwide. And so these are the ozone, PM2.5 and PM10 are particulate matter. The 2.5 means diameters less than 2.5 microns. 10 means diameters less than 10 microns. And these are in units of micrograms per meter cubed. And so you can see what these various values are. Notice these values for PM2.5 and PM10 of annual means of 10 and 20 micrograms per meter cubed. And it sets these guidelines based on reviews of health effects of these various pollutants. Yeah.
So does that mean that the PM2.5 is worse than the PM10 because it's even smaller than...
Yeah. I mean, penetration is greater. I mean, the problems with particulate matter in terms of health is penetration into the lungs. And there is more concern about PM2.5 and even smaller aerosol because of the greater penetration. So much of the earlier legislation was done on the basis of PM10 because that was easier to measure. But increasingly, we're moving towards PM2.5 in legislation. So the guidelines indicate that by reducing particulate matter pollution from 70 to 20 micrograms per cubic meter, we can cut air quality-related deaths by around 15%. Air quality-related deaths are remarkably substantial. We don't tend to think of them as causing death. But they do. It's been calculated in the UK that the average reduction in life expectancy, the average reduction in life expectancy is of the order of 6 months. And for some people, they're going to be much more affected. People with lung problems are going to be much more affected by particulate matter, for example, and so their life expectancy is significantly reduced. So it is a very substantial problem. And it costs a lot. If you look at the costs of healthcare in the UK, just in the UK, from the effects of the impact of air quality problems on healthcare in the UK, the annual costs are of the order of somewhere between 20 and 30 billion US dollars. So it's a lot of money. So there are clear advantages in improving air quality. Yeah?
Are there good studies for Asian countries for air quality?
Yeah, they're getting better and better and better. I'll show you in a minute.
Why can't 2.5? Why can't the last 1.5?
Yeah, it's what would be good in many ways would be to have PM1, but the way in which what happens is you have monitoring programs. So throughout a country, you have large numbers of of stations which are measuring these quantities. And PM1 is much harder to do than PM2.5. PM2.5 is harder to do than PM10. And so it's a cost issue. So you can, if you're interested in what's going on in the US, then you can find you can't read this, but you can go and look at the website, and you can find there what the US controls are on air pollutants. Use of satellite measurements to understand emissions. Now, this is work done by this guy, Daniel Jacob, and what they did was to use satellite measurements to understand emissions of various compounds, and especially in the US of isoprene. And what they did was the satellites measure formaldehyde. Formaldehyde is produced. This is not a slide that I've given you. I'll include this in the final. Sorry, I didn't put a star on it. I'll include this in the final printing. Well, the final web version. So isoprene reacts very rapidly, and so the formaldehyde is produced very close to source. And so if you have a satellite measurement of formaldehyde, then if isoprene is the main precursor of formaldehyde, which it is in heavily forested areas, if isoprene is the main source of formaldehyde, then you can infer from the formaldehyde how much isoprene was emitted. And so that's what was done here. So these are the emissions of isoprene that are calculated using a model for isoprene emissions and for degrees of forestation. This is the satellite measurements of formaldehyde, and this is the geoschem measurements of formaldehyde. And so from this, they can infer the isoprene concentrations and use that to test these emissions inventories that are generated. And these emissions inventories are important because obviously they go into regional and global models, remembering how important VOC emissions are. But what I want to show you are calculations that were done for Asia. And so these are what are called bottom-up inventories, whereby what people do is to estimate the amount of different processes occurring that lead to emissions of hydrocarbons. So this could be road transport, it could be, for anthropogenic processes, it could be road transport. Solvents. Solvents are a very important source of VOCs. Paint, for example, leads to a lot of VOC formation, surprisingly large amounts. So these are anthropogenic sources, and these are from bottom-up inventories predicted. This is biomass burning, and these are biogenic emissions. So you can see these large biogenic emissions of hydrocarbons down in Southeast Asia. And here's the total. And then these are GOME measurements. GOME is a satellite that's measuring the spatial distribution of formaldehyde. So you can see these are the inferences that were made from formaldehyde and using the model, using a regional model, a global model of relating the formaldehyde measurements to the amount of VOCs that are present. And you can see in China up here, then there are substantially more emissions than are predicted from this bottom-up inventory, especially, well, for most activities, but especially for biomass burning. And this is something called satellite hotspot counts. So this is looking for hotspots detected by satellites. This is in northeast China here, these very large numbers of satellite hotspots. And it corresponds to the winter wheat harvest in China. And what happens in China, and this used to happen in Oregon, for example, is that after harvest, the fields are burned. So there's stubble burning in the fields, and this gives rise to substantial emissions. And that's what's giving rise to these hotspots, but it's also giving rise to emissions of VOCs from basically biomass burning, but these are not forests, these are fields. And here you can see the consequences of that. So these are monthly mean afternoon surface ozone concentrations simulated by a global model, GeosChem, using bottom-up inventories. So if we look in June, there is a certain amount of ozone, quite a bit of ozone, but these are then the differences if you use these GOEM measurements. If you infer the VOC emissions from the GOEM measurements and then calculate the ozone formation from that. And you can see, so these are differences, and these are differences of the order of 20 parts per billion in ozone occurring in this region of northeast China and deriving primarily from this biomass burning. Sorry.
What is the negative scale? Is this like a log scale?
So yes, no. This is the difference between, this down here is the difference between the model results with the bottom-up inventories and the model results with the VOCs inferred from the formaldehyde measurements. So what the message is for China is that by controlling stubble burning in the fields, they could substantially improve their ozone concentrations in this region of northeast China. The problem is that stubble burning is a very useful way of moving through from one season to another in agricultural terms. So remember what we said about, these are PM10 measurements. Remember what we said about PM10, about annual means from WHO being, the upper limits being of the order of 20 micrograms per meter cubed. Look at these values here. So 508 micrograms per meter cubed in Macedonia. Substantial values throughout much of Asia. And so I also mentioned the problems, the cost of the problems of particulate matter in the UK. And you can see that the health impacts of these very high loadings of PM10 are very large indeed. Where does this PM10, PM2.5 come from? These are PM10 measurements in, again, I'm sorry, this isn't a slide that you've got. I put it in this morning. But I'll include it in the final version. So these are measurements of PM10 in the UK, and these are roadside measurements. And these are urban background measurements. So this is in an urban region, but moving away from main traffic sources. And these are rural values out here. And you can see that the PM10 values are not all that different. The UK is a small place, and you don't have to go very far from one town to another. But nevertheless, these are genuinely rural measurements here. Okay, the horizontal line that's the average. No, sorry. These are different sites. It is basically a histogram. Yeah. These are many measurements at different locations. Sorry, I should really have explained that. These are measurements, values at different locations throughout the UK. These are from monitoring stations which are roadside. These are monitoring stations which are urban background, and these are monitoring stations, which are in rural communities. And then these horizontal lines here are the averages for those. And you can see that the averages don't change all that much going from roadside locations in cities to these rural locations. And so this shows you the origins. So this is going across London now. So this is a histogram of PM10 concentrations going across London at different monitoring sites as we move across here. And these are the origins of the particulate matter. So this is the background that's coming from a long way away. This is secondary aerosol, and then these are the aerosol that's generated in the region. This is to the west of London, very high value. Any suggestions where that might be? Anybody who knows London? Well, that's Heathrow. That's around the airport. So large amounts of particulate matter generated near the airport, not just from, and in fact primarily not from aircraft, but from vehicles converging on Heathrow. But the key thing from this is that secondary aerosol is very important in determining the overall levels. So that's why these rural areas are almost as bad as the urban areas, because of secondary aerosol formation. And we talked a little bit about this yesterday. This again is a slide which I put in this morning. And what it's telling us is that if we want to model, this is aerosol formed from organic compounds. And what happens is that, let's just discuss briefly where the aerosol comes from. We have emissions from vehicles, which is mainly soot type species. There are other sources such as desert dust, so wind-blown particulate matter and this is a big problem, especially in the Mediterranean area, as far as Europe is concerned, with sand blown from the deserts in North Africa. And also sea salt. So sea salt, if you get spray in the sea, then sea salt gets lifted into the atmosphere, and that again is an important source, primary source of particulate matter. But then we get secondary sources, and we have NO2, which gets oxidized to nitric acid, taken up by aerosol and forms nitrate, and that adds to the aerosol mass. So we get secondary aerosol coming from nitrate, which was formed from NOx. And then we get secondary aerosol formed from organic matter. And there's a very, this is not well understood, but there's a very interesting, if you're a chemist, there's a very interesting chemical problem there. So this diagram down here is telling us about what happens if we take a given compound, a given organic compound, and oxidize it in the atmosphere. And one of the things that happens is that organic compound, as we'll see, gets broken up and forms eventually carbon dioxide and water. But there is another thing that can happen, and that is that we can add more and more oxygen to the molecule. So OH adds to the species, it then gets oxidized, and instead of breaking up, it adds a carbonyl group or something. And so what happens is you increase the O to C ratio in the molecule, and it becomes more and more polar. And that enables it to condense more easily onto aerosol. And so there's this competition occurring in the atmosphere that we really don't understand in the detail we need to do about, on the one hand, the fragmentation process, and then the other, what's called the functionalization process, whereby you make the VOCs more and more polar and therefore more and more able to condense. And the secondary organic aerosol component of the secondary organic component of aerosols is really very substantial. It can be as much as as 50, 60%. Okay, briefly, these are more satellite measurements now of NO2 over China. And you can see these large concentrations. And these are NO2 columns determined, so this is the total amount of NO2 all the way up to the satellite. The bulk of it is down close to the ground. And so these are the way in which the concentrations changed over this period, 96 to 2002. And so the US has been fairly constant. Poland down here has decreased. Western Europe has decreased. But here we've got Hong Kong and East Central China, where the NO2 is increasing because of the massive industrialization which has taken place and is continuing to take place in China. And that's why those controls in China are so important. There are going to be there's clearly going to be a continuation, although it's slowed to some extent, of the industrialization of China. I was in China 2 weeks ago, and the amount of building that's going on is absolutely amazing, and as many of you will know. So this is one of the problems of what's happening throughout the globe, of the differences in the way in which NOx emissions are changing throughout the globe. And it's important regionally, but it's also important globally. And so these are satellite measurements of NO2 over East Central China, and you can see this gradual increase over this period of time. Okay, let's finish there, and then let's try and get back by 11:15 on the dot.